Today, I'd like to talk about our digital implementation flow for highly reliable automotive design using the Fusion compiler. This is today's agenda. There are four topics. At first, I'd like to introduce our company, Renesas, using the marketing slide. And I will talk about the automotive solution. And I'd like to talk about our design challenges for the automotive LSI. And I will explain how important for us to implement the high reliability for the automotive LSI. And next, I'd like to show two key technologies for the high reliability. These are robust cell and fail-safe implementation. We introduced a Fusion compiler to realize these two key techniques very effectively. And I will show some real results on our design R-Car and RH50. And finally, I will summarize my presentation. Now, I'd like to introduce our company, Renesas. We are a solution provider. Our goal is to make every endpoint intelligent by offering a product solution covering from the automotive through the industrial and broad-based area. In the automotive area, our products contribute to the eco-friendly electric vehicle and comfortable connected cars and safe and secure autonomous driving. In the industrial and broad-based area, our products contribute to realize smart factory, smart living, and infrastructure, enabling the flexibility, safety, and secure. Today, I'd like to discuss this automotive area. This slide shows about our automotive solutions. We are focusing on open, innovative, trusted solution for the future driving. We are leading supplier for the automotive MCU and SoC, and our quality of our product is extremely high. We use advanced process technology, and we providing the highly valued system by digital computing with analog solutions as well. The right picture shows a profile of our automotive LSI. The R-Car is covering the in-vehicle infotainment system, such as navigation, integrated cockpit, connectivity, and ADAS. And our MCU product, so-called RH850, is controlling the in-vehicle controlling system, and the family is widely used in many areas in automobile. Now, please think about your automotive vehicle. What is the most important? I think you need a high performance, or better efficiency, or ease of use. But first of all, we think the automotive vehicle should be certain. This table describes the expectation for the consumer electronics product and the automotive vehicle. At first, the lifetime of the consumer product is up to 7 years. But automotive vehicle is expected to work for more than 10 years. And then expected usage also different. In general, consumer product is designed as indoor usage and under 100 Celsius degree temperature and a stable condition. On the other hand, automotive vehicles should work at more than 150 degree temperature and unstable condition. This because it is moving outside. And the most important thing is keeping you safe. The automotive vehicle is expected to protect you from any dangerous situation on the road. Therefore, we think the MCU and SoC in the automotive vehicle should work for a long time, and they should recover to save human life if something wrong could be happen. Therefore, we put all of our effort to make a high reliability in the automotive area. Now, I'd like to explain our design challenges for the automotive LSI. As you know, recently, many functions are required for the automotive area. The multi-camera and radar and the LiDAR are key functions for the semi or auto driving systems such as ADAS. And then connectivity between the several vehicles is expected with a 5G system. And security and human interface is essential for the automotive driving. Therefore, we need to put many functions in one automotive LSI. The right picture shows the trend of the required function for the automotive LSI. As you can see, the required function is increased and more complicated. We covered these requirements with our product, ARCA SoC and RH50. The ARCA H3M3 E3 enables the automotive computing platform for the autonomous driving, and the RH50 E2 is a high performance and very low power MCU, and the coming U2 offers high scalability, high integrity, and rich program capacity. But remember, we need to keep high reliability for these LSI. Every single function must continue to work over 10 years. Therefore, our challenge is meeting such high reliability for function-rich ARCA and RH50. Before getting into the detail about our design methodology, I'd like to let me briefly explain about the long history of the collaboration with Synopsys. This chart shows how our design methodology has been improved from the 2000 in order to solve our design challenges. As you can see, there are a lot of success collaboration in the digital implementation area. In early 2000, we had launched the physical aware synthesis with design compiler SPG. It gave us a good timing correlation between logic and layout. And I think we are one of the first semiconductor vendors to introduce ICC2 in our flow. In order to improve our design QoR, we established many good methodology using a DCG and ICC2. Now we introduce a Fusion compiler. The Fusion compiler offers a unified flow from RTL to GDS. It is a very important feature since we don't need to worry about any correlation issue between the logic and layout anymore. And I will explain later, but this single pass optimization is a key point to make a highly reliable automotive LSI. Now, from next, I'd like to explain how we can achieve the highly reliable automotive LSI using the Synopsys Fusion compiler. This slide shows two key techniques to achieve the high reliability of the automotive LSI. One is failure prevention with our robust cell. Second approach is a failure detection with our fail-safe structure implementation. I will explain each of them in detail. The first approach is a failure prevention with our robust cell. As you can see in the left picture, the common most failure modes are leakage current, TDDB, and hot carrier injection. To prevent such most failure modes, we prepare the standard cell with lower failure rate in most devices. We call this type of cell as a robust cell. So to prevent the failure, of course, we'd like to maximize the usage of the robust cell. However, there is a problem. The right graph shows the cell characteristic of the characteristics between the cell speed and the robustness of the cell. As you can see, in case of the more robust, then cell speed becomes slower. Then, if we just use a robust cell, we cannot meet that PPA target. Therefore, for prevention of the most device failure, effective usage of the robust cell is very important through the logic synthesis and optimization of the layout. In a conventional approach, we swap the robust cell in non-timing critical paths at each of the design steps, as shown in this left picture. It doesn't hurt the timing closure of each step. However, it may not use the robust cell effectively. Now we introduce a fusion compiler. With Synopsys, we co-developed a new single costing with a robust cell usage all through the design step. With this total optimization flow, we can utilize the robust cell effectively. These graphs show the comparison results of the cell usage between the conventional approach and our new approach. In each graph, left shows the cell usage ratio with a conventional approach, and right bar shows the result with our approach. Blue color means more robust, and red color means less robust. And then please note that robustness is measured with our own calculation. Now, please take a look at the peripheral and bus logic case. In the peripheral logic and bus logic, this is come from the RH50 MCU, but this block, the timing is not so critical. Therefore, even with a post-cell swapping approach, the blue color cell, robust cell usage is better, many. Therefore, improvement with our new approach is limited. The interesting thing happened on the CPU core and then graphics core. With the conventional approach, the red color cell can be minimized. However, the pink color cell usage of the pink color cell is still many because they cannot replace to the robust cell in order to meet the timing. With our new approach, the balance of the cell usage is much better. As a result, we can achieve the 25 more robust CPU core for the RH50 MCU and 39% robust CPU core for the R-Car SoC. And in a graphics core case, some particular path is very critical in terms of the timing. In a conventional approach, many robust cells are used. However, red color cells still remain for the timing closure for such critical paths. With our new methodology, the balance of the cell usage is much better. The blue color cell itself is less than the conventional approach. However, we can minimize the red color cell. As a result, we can achieve the 25 more robust graphic core for the R-Car design. These results prove that our single costing approach is very effective for the effective robust cell usage, and it can improve the reliability of our design, RH50 MCU, and R-Car SoC. The second approach is failure detection. First approach is failure prevention. Next one is we need to detect the failure. As you can see the left picture, the redundant logic structure, such as a dual lock step, is widely used for the failure detection. The idea is just preparing the redundant module and then comparing the primary. The occurrence of the error can be detected as a state after comparing the values of the primary and redundant modules. In order to guarantee the strong isolation of the redundant module, we need to separate primary and redundant module physically, as shown in this picture. Of course, this physical separation causes a lot of overhead in the layouts because there are a lot of connection between the primary and redundant module. Now, please take a look at the right graph. The right graph shows a trend of the number of redundant modules in one automotive LSI. As I mentioned earlier, many functions are need to be implemented one automotive LSI, then the number of redundant modules also increase. Again, there are a lot of connection between the primary and the redundant module. The floor plan with such many physical separation affects the final QOR and design turnaround time. Therefore, we need a smart implementation methodology for these physical separation in the automotive LSI area. In a conventional approach, we just manually create a floor plan as shown in the left picture. As you can see, we make many bounds to control the location or layout of the primary and the redundant module. It becomes very tough to satisfy the PPA target if we need 100 separate modules. Now we introduce a fusion compiler. With Synopsys, we co-developed the automatic implementation and check function for this physical separation. As you can see the right picture, without any bounds, the fusion compiler automatically found a good location for the primary and redundant module. This table shows the comparison results to our RH50 MCU with manual floor plan and even the no constraint case of the ARCA design. We compare the congestion, timing, cell area, and the overhead of the floor plan creation. With the fusion compiler automatic solution, we can get a comparable result for all items, all categories. And the important thing is we can eliminate the floor plan creation overhead. In case of the chip top of the RH50 MCU, there are many modules need to be separated. Therefore, we need to spend more than 1 month to create a good floor plan to meet the PPA target. Now, with Fusion Compiler, we can eliminate them at all. Similar thing can be seen in a CPU core. We think this is a significant improvement for the implementation of the automotive LSI. Finally, I'd like to summarize my presentation. The meeting high reliability requirement is an increasing challenge for our automotive LSI, such as RH50 MCU, and ARCA SoC. And we have a long history of the collaboration with Synopsys to develop a new design methodology to address such kind of tough challenges. As I presented today, our new methodology with the Fusion Compiler delivers a more robust LSI of the ARCA and RH50 with very short turnaround time. And we will continue to innovate the new design technology, such as machine learning, incorporate with the Synopsys. And with these activities and collaboration, we continuously deliver the highly reliable automotive LSI in the future. Thank you very much. That's all my presentation.